with cures by Professor Thompson in differential geometry and coloring of manifolds. Please.
Which I think you prefer to keep this in Billy Joel. So far we talked about smooth structures, so I now want to talk about Riemannian geometry. This is the sheet, which you'll see very quickly. It's a fact that on any smooth manifold you can introduce always metric on a smooth manifold. This requires the topological spaces, current compact. All spaces we're interested in will have the properties so that this is actually true. So it's a Riemannian metric, which means it's a Euclidean signature. Somebody asked me yesterday what happens if you want Lorentzian signatures, and I said you need a nowhere vanishing vector field, and that's the same. That's actually a condition. So if there's restrictions on manifolds, not all manifolds have nowhere vanishing vector fields. So for Euclidean signature, you can always find one. For Lorentzian signature, you may have to work hard. Not all metrics are equivalent, so we should really always write down something like this to indicate the thing that we're really talking about, that is the manifold and the metric that we have in question. Unless I say so, everything I'm going to be talking about will be Euclidean until I actually very explicitly say Lorentz. Right? So until then, it's all Euclidean. So the part that I need for today, the metric, is a thing which is known as the Hodge-Star operator. So, can you read this now? Can you read my writing? Hodge-Star. And basically, there are a number of ways of defining it. I'll give you 1.5 ways of defining it. So basically the idea is it's an operator, it's a star, so we'll call it a star. And it's a map from p forms that can be complex valued into n minus p forms. That real to you, and the dimension, the real dimension of x is n. So this is an extra structure above the fact that we have a smooth manifold. We have completely inequivalent metrics. So it's, we start with the topological space, then we have smooth structures, and now we have metrics on them. Okay? So they're all different. You have to keep in mind they're all different. So it's a map like that. The way we're going to define it is a bit obtuse. So definition, the Riemannian volume, this for all of you. Who's done general relativity? So you all know what I'm talking about more or less, right? The Riemannian volume, so the Riemannian measure, let's say. Measure EVG, I've put the G there, that's the same G as that one, of XG is defined to be EVG equals root G in X. Alright, this looks really familiar for those who have done G here. Whenever one writes just a G like that inside square root, what they really mean is the determinant of G, and they mean the determinant of G with both labels down. All right, so a metric, remember a metric is basically something that equals G new tensor dx new, and it's symmetric. This guy, remember, metric is always like. And when you write G here, like this, what you really mean is the square root of the determinant of G, D, and X. And you'll notice that I disagree with the sign that was being used yesterday, and that's because I'm in Euclidean space. Okay? So that's the only difference. Definition. Alpha, beta, P forms, complex value, and then we set alpha, beta at point X to equal the sum of alpha u1. Remember, alpha has, there's probably a 1 over P factorial here, you have to forgive me. Like I said, I'm adopting Nathan's normalization conditions, so put any number you like there. And then we take beta bar, so we have u1 to up, and we have g u1 u1 to g up up. So this is a pointwise scalar product. The bar is there for reasons which will become apparent pretty quickly. And, well, okay, like that. And it makes sense to have a bar because we have considering complex forms at this point. So here's an exercise for you. I'm supposed to give you homework, I forgot. Did I ask you to do this yesterday? Show d squared equals 0?
Yes.
Did you do it? Not yet. You did it last night. All right. Did you figure out how to do it? Tell me, please. That's easy. You'll like that. Anyway, so for alpha, which is in omega p xc, you can show that alpha at point x is in the reals, and if it happens to also be point x, then you can show that it's in the positive line. This means So that's useful because if you just restrict, first of all, it makes it real, that's a good thing. Secondly, if it's in the reals itself, then this is positive definite, semi-definite in a product pointwise. So that's what you've got to do. Here's a definition. Hodge star hasn't appeared yet, I'm just giving you a lot of stuff before we get there. The inner product, so I'll define an inner product. That's new. That wasn't there yesterday. There was a board in front of it. Okay, inner product for alpha, beta, which are now in omega p xc. Remember, these are complex, and this is not the pointwise inner product, but this is now the inner product, which is defined on the entire space. And the way you define it. You know, for those of you who've done general relativity, you understand that this is exactly the way you would write any action. Write an action as the integral over x, square root of g, dnx, and then some scalar, right? That's what you always write. This is giving us a scalar, pointwise, every point. That's the measure that we usually use. It's just a silly way of writing. So here's my first definition of Hodge star. star 1. The Hodge star is the unique map star, which is omega p x c to omega n minus p x c. Sorry, that's an n. See that? C. So it's unique. So that for any beta, which is an element of omega p xc, alpha wedge star beta, right? I can wedge any form. Beta is a form here, star beta is a form there. I can wedge it. And this is supposed to equal alpha beta evaluated at the point x times the volume form for all alpha which are in omega p. Alright, so pick a beta, any beta you like, and this must be true for all alpha. And then that's unique. Definition number 1. That was fun. Definition number 2. And that's given star is the map which just does, I have dx mu1 wedge dx mu p, then this is the same as the square root of g over n minus p factorial of epsilon mu1 to mu p, mu, okay, called mu p plus 1 up to mu n dx mu plus 1 wedge dx mu n. And the epsilon symbol is the totally antisymmetric tensor which you can have on any space. It's a density, and it has the following properties. Epsilon mu1 up to mu n is equal to 1 for any even permutation, 0 two indices agree, and minus 1 for an odd permutation of the indices. All right. Now, it may not look like it, but those two definitions actually agree. It's useful to have both. Because it makes things obvious. See, it makes the fact that this is, if alpha and beta are real, it makes this obvious that this is always positive. Right? Because you've got the inner product there, and you've just proven by today's homework that this is always positive semidefinite. This definition makes it obvious that star depends on the orientation, because it depends on whether you think that you orientate your manifold with dx wedge dy or dy wedge dx. They're not the same, right? They differ by a sign. So the two definitions help. I'm not going to need any of that. I'm actually only going to need this. So here's a proposition. Oh, you're going to need this. And the proposition is the following one. Star squared on omega px maps you to omega px. That's obvious. Because if you look at the definition, star maps omega p to omega n minus p. And then if I act again with star, I get n minus of n minus p, the n's cancel, I get plus p. So it's a map from omega squared is a map from star squared is a map from omega t to omega p. And in fact, on omega p, it turns out that star squared is equal to minus 1 p n minus p.
Which product between alpha and plus beta?
Yes. Yes. Yes, there is. That's the wedge. Sorry, if you can't read my writing, try to make me magnify it, and then I'll go back down and then make you do it again. All right. So in particular, what do you notice about this? It's not 0 anywhere because it's just plus or minus 1, which means it's invertible. So you've just proven, i.e., star is an invertible map. We've got an invertible map between two spaces. They are isomorphic, right? Two vector spaces. So we've just given ourselves an isomorphism This isomorphism depends on the metric we chose, but nevertheless, it's an isomorphism, okay? If you choose a different metric, we'll get a different isomorphism, but it doesn't matter. We've got one. We're happy. These two spaces are not at all different. Well, they are. They're not so different. That was the good news. What was your homework? Oh yeah, homework. Exercise. Prove proposition. That's a combinatoric nightmare. If I were you, I'd start in low dimensions and just be sure that it works, okay? Okay, so we did all that. So now, let me state a theorem. By the way, I should tell you, I'm not a mathematician. I use words like definition, theorems, propositions, and so on as placekeepers for me. It just makes it easy to see what's going on, all right? So don't be too scared about these words. So theorem. The inner product for alpha, notice I'm choosing R, I'm not choosing C. I'm really taking the reals here. Is positive semi-definite. All right, so that means the following. It means this is the inner product, not the pointwise inner product. This too is an element of R plus. And the truth of that is a bit boring. X is compact, closed, means nothing diverges here, it's almost infinite. This is positive, volumes are always positive. If I integrate something positive, I get something negative. It doesn't happen, right? So, where X is, so I've taken X to be compact, closed. And everybody inside is smooth. As an exercise. So there's nothing to do. You just look at the formula and everything, you're integrating something which is positive. So as an exercise, star 1 equals EG. That's a trivial exercise, but it's good to know because it reminds you that 1 is a 0 form. Star 1 is, so it's P is 0, that's one more. P is 0 go up to omega n. The volume form is a top form. Right? I wrote it down somewhere before. It's gone, it's not of it. All right. So star 1 gives me the natural top form. That reminds you that the metric is really hiding in this formula because the metric is really over there. It's a good thing. you've got a metric, you can actually go and do something else. Just look at adjoints of D. We have an inner product. So here's my definition. Well, it's not mine. So D alpha beta is by definition, yeah. It's exactly the right moment, thank you. It's a great formula. So that's a definition of the adjoint of D. So that's delta is the adjoint. Right. And it's not very hard to show. Delta is actually equal to minus, well, I'll say NP plus N plus 1 star D star. These are compositions of maps where this is acting on a P-form. You should really have a good look at this. This inner product only makes sense if the entries have got the same degree, right? So if you look over here, the inner product requires that I can actually do this. One of these guys has got more labels, I can't do it. So they must have the same number of labels and be of the same degree. So if alpha is a P-form here, so alpha is an element of omega P, where is D alpha? It's just a map to omega P plus 1. So D alpha is an element of omega P. Don't worry about the fact that it's a differential map. It's a still map. Omega P plus 1. So the only way we're going to get an inner product here is if beta is an element of omega P plus 1. All right. So beta must be an element of omega P plus 1. So if we have a look over here, this is an element of omega
B.
So this thing must be an element of omega
B.
Aha, you're getting it. So beta is an element of omega P plus 1, so what are you going to tell me about delta? Where does it map? Omega P. Otherwise none of this makes sense, so here we go. So this is great. D is increasing the degree of the form. Delta is decreasing the degree of the form. Okay. Exercise. Exercise. Prove. Start. If you don't worry about the sign, this is actually trivial. Okay. Why is it trivial? Actually, I haven't really given, yes, I've given you the formula. Use this. Proof that. Use alpha beta for, let's call it gamma, is equal to the integral of alpha wedge star gamma. Oh. Sorry. There's a missing bar there. Do this over the reals, otherwise I'll get myself into trouble. No, don't want to correct it now. So just concentrate on omega px. I'll fix the signs later. Fix conjugates later. Okay. So, okay. The inner product is this. This is a definition. I can now just point that over to there, and then you've got it. All right. So what does delta do? I mean, if it lowers the form, So let's ask ourselves, well, on functions for us are guys like this, right? Now, what's omega to the minus 1? Nothing. Zero. So it's null. It's basically the empty set, right? There's nothing in there. And so acting on functions, we know exactly what delta does. It kills it. More function. Dead. Gone. No more function. So that's gone. What does it do to one forms? So one forms, just so you get the hang of it. Let's take A to be an element of omega 1 x c. It's got to go into omega 0 x c. And it's got to be covariant because everything that we've done is covariant. But this is a set of functions. It's also got the derivative operator in it. So A mu dx mu actually goes to the covariant derivative of A mu. It's the only way I've created a function. You could have guessed this just by covariance. If you work out the details, you'll find that this is true. Yes, please.
So this formula, mixing the internal product with the exterior one, do you need to include the complex conjugate of beta in the left-hand side?
Yeah, that's what I want. That's what I wanted to say. I didn't want to get into that. So yes, there should be a complex conjugate there. That's why I said over here, just take it to be real. But you're right.
But why do you want to write down this way? No, in the left.
It doesn't matter.
Okay.
All right.
Excuse me, the last symbol, the is a common gradient?
No. So yes, thank you. So this is the covariant derivative with respect to the Levi-Civita connection. So do you know what that is? No. Right. Do you know what a Christoffel symbol is?
What?
Christoffel symbol.
Yes.
Good. That's it. So basically it means the following. It means the covariant derivative acting on a one form would be, somebody correct my signs, mine's acting on
Is the covariant derivative?
yes, and I think it's a minus in this case. Something like that. That'll work.
So we're working with portion B.
Yes. Everything in this case is just with metric, which is itself. I haven't defined torsion. I haven't defined an end bind, for example, to sort of measure it. So, but if you just look through it, you'll find that that's what it does. So I hope I got my factors right. So if I put the label down, it doesn't matter. Just let me leave it like that. The sign's right. You can fix it. Okay.
Professor,
Would you stop calling me professor, please? Just George, you'll do.
okay, George. The D of the Jacobi D with the superindex mu, what does it mean exactly?
Which one?
At the end?
Gamma.
No, the Jacobi's D. Yeah, you were near. Yes, there.
Partial derivative?
It's a partial common derivative?
Yes. So let me write it in detail. So when you write something like D mu A mu, you really mean G mu D mu A mu, right? So what you really mean is G mu mu A mu
Oh, okay.
George? You're George too?
Can you use other connections besides that one?
You can, but I won't, because this one that pops out of the definition at the start. You see, what happens here is that you've got the metric hidden away over here in a very particular way. So what you get is the Christoffels. Anyway.
But that connection implies that the covariance derivative of the metric is zero. But
With that connection.
with that connection, but what exactly concept do we introduce this connection?
No, I get it just by following the rules through. Do me a favor. Just so I can stop this discussion. Take this, act it on a 1-4 in 2 dimensions, just to make your life easy, right? So you don't have a lot of silence to worry about. And then just see what you get. If you don't get this, complain. And if you don't get it, I'll complain. It's okay. Right, so I'm moving on. So what I want to talk about now are Laplacians. We've got everything we need for Laplacians. So let's worry about that definition. So now we can talk about Laplacians. On forms. This is nice because Laplacians on forms are much easier to write down than on horrible extensors. So there's simplicity here. And here's my definition. You like it, I think. Definition. The Laplacian delta on a form of any degree is delta equals d, little delta plus little delta d. That's it. That's a Laplacian. So one immediate consequence of this is that on a compact closed manifold, the spectrum is actually real and semi-definite. So I'll prove that for you. So here we go. Let's prove it. Here. X compact, closed. Remember, closed means no boundary. Closed, Riemann-Riemannian, which means that I've already made a mistake because I can't write it like that, can I? I must write it like that. I've got to tell you with respect to which metric I'm talking about, so I should write it like that. The spectrum of delta is real and positive semi-definite. So here's the proof. Homework? No. We'll actually do this one. I'll leave the hard stuff for homework and easy stuff I can do on the board. So
What do you mean by spectrum?
eigenvalues. Where was the question? Was yours? Yeah, good question. Yeah, yeah, eigenvalues. But it does. I mean, somehow it really does come from the idea of spectrum of light frequencies. So the spectrum. So let d omega equal lambda omega. So omega is some p form. So let's sit here for the moment. And I'm going to take everybody in R. Okay, so I should actually tell you everything is in R. If I want to do C, I'll talk about it in a nearby lecture. All right, so we're trying to say something about these guys, right? The spectrum are the set of the eigenvalues. So we want to say something about the lambdas. So one thing we can say about the lambdas is that they equal omega, delta omega divided by omega omega. How did I do that? I did that by simply taking the inner product on the right-hand side with omega. Sorry. Damn. I'm silly. There's something I didn't tell you. Okay. Outside of the proof, let's do it here. Delta maps omega p to omega p. And the reason for that is that this raises the degree by 1, but that guy lowers the degree by 1. This lowers the degree by 1, but that guy raises the degree by 1. So nothing changes. It's a map, again, but from omega p to omega p. All right. Sorry about that. So I can take the inner product of omega with delta omega, and I can take the inner product of omega with itself, of course. And providing omega is not 0, which is not, we don't usually look at the spectrum of the 0 vector. It's a bit boring, so we won't do that. So providing omega is not 0, we actually, this formula makes sense, right? Like I said, you just take the inner product of omega here, omega there, lambda is a number. In the definition of the inner product, lambda comes out of the inner product. And you can write this formula down. So, we know something else. Delta is equal to d delta plus delta d. Our inner product is linear, right, the way we wrote it. So we have that lambda is actually equal to d omega over omega omega plus del omega over omega. Now, you might say, how do I know? Well, the answer is just put it in. Take the first term here. Right? So I take that term and I put it here, d delta. By definition, d of anything, I can move to the other side. It becomes delta, so I get delta delta, which is that term there. I'll look at this term here, I get delta d. If I take the delta to the other side, sitting over here, right, I get d d. Yes? Then, it's a positive semi-definite inner product. The only way it can be 0 is if the form is 0. That was something you were proving. So this is not 0 because we took omega not to be 0. So this is either 0 or positive. And this is either 0 or positive. So there we go, finished. It's great, isn't it? So the only way we can get lambda equals 0 is if that happens. And for lambda equals 0, what we're saying is that del omega equals 0. So we have that. Okay. Forms which, these are special, and I'll tell you, I'll give you an indication straight away of why they're special. These are called harmonic forms. And there are some very nice theorems which tell us that they are very, very useful So let me
Sorry, Dr. Thompson?
just George.
Okay, George.
No, just George.
Okay. So what does that mean that dW is equal to 0? I mean,
Where?
I know that delta W
Here.
maps from P plus 1 to P, but D maps from P.
Right, that's right. It
So
does,
P plus
in
one.
both senses, it's in the kernel of these two different maps. Exactly. It's 0 in both senses. So if I set it for A, and then I said delta A is 0, you would tell me that the covariant gradient of the A was 0. It's one way, down. And you'd also tell me that the dA, which is F, is 0. So if I was doing gauge theory, I would say I had a field strength which was 0, and a gauge field which is gauge fixed. In the Lorentz gauge. This is the Lorentz gauge. And you don't mind, because Nadain told you that you could do that.
Yeah.
Okay? Right, so it's 0, it's in the kernel of both of those maps. How are we doing for time?
10.
It's terrible. Okay, so skip that. Right, so if you work it out, I'll give you a real formula tomorrow probably. Or if you work it out, you find that the Laplacian is basically what you would have thought it was, something like this, plus higher order terms which would depend on the Ricci and the Riemann tensor. Okay? And that's it. Now, you might be worried about my sign. I mean, after all, I told you that del is very positive. All its eigenvalues are positive. And the first thing I do to you is I throw in a minus sign, which seems really unfair. Okay? But that sign's correct. And a very good way of understanding that sign is correct is to always think of your quantum mechanics. And in quantum mechanics, everything you care about is plane waves, more or less. So what happens if I act with, now just think of these as partial derivatives. What happens if I act with two derivatives on a plane wave? It gives me a minus p squared. I'm in Euclidean space, so p squared is positive. So this is correct. This sign is actually correct. It might not be so correct, depending on your conventions in Lorentz space, right? So you have to be a bit careful. But we're in Euclidean space here, so everything is fine. So you're not worried by that. Now, let me throw another theorem at you. So I have a nice Riemannian manifold, and I want to find out what happens if I change my metric, where t is an element of 0 to infinity. T can't be 0 because then my metric would be degenerate. It can't be negative because I don't allow metrics. So it must be like this, right? So take t to live in here. And I ask a simple question, which is, what is the relationship between del t and, well, now that I've written it that way, what's the relationship between the metric, the covariant Laplacian with metric tg and the Laplacian with g? And the answer is, it's very easy to figure it out. The relationship is that this is equal to t to the minus 1 delta.
Sorry?
And I'll leave that as homework.
P is constant, right?
It is constant.
Sorry, a question. In which part of the demonstration we took into account that the manifold was closed and compact?
Aha!
Aha.
Aha, very good. I integrated by parts. I integrated by parts.
I don't see it.
Okay. One-dimensional integral. FDG. This is not minus dfg unless this happens, unless they happen to vanish at the boundaries, or it's compact. Right? Circle, on a circle, for example, on S1, this is an equality. On the interval, I would actually have to subtract off the value of f and g from a to b, whatever it happens to be. So I've used this to define everything. I want to be able to integrate the parts.
Okay.
Thank you.
Also, maybe this is also need to implement that the mesures are defined, but the integral is not necessarily well defined in every method.
No, so that's why I said these are smooth-oriented manifolds. Now, in fact, I want to go back to that. Thank you. I want to go back to that because it's not enough time in the day. But part of the problem is that I said that the star operator depends on the orientation. It depends very strongly on whether I have the x wedge dy or I have dy wedge dx as the positive measure. Okay? So, hang on. And so, if your space is not orientable, there's a problem. If you change the orientation, you change the sign of the star operator. You have to be very careful. But once the game we're playing is we fix the orientation, it's God-given, it's oriented, it's just there. Okay? Sorry.
Just as a comment, you use the fact that the manifold has no boundary to integrate by parts, but you use the fact that the manifold is compact, first of all, to ensure that you can integrate over it,
Yes.
and that these integrals will converge. Just
Okay, thank you.
Thank you. Yeah, so I mean, technically these are L2, basically. This is where it's sitting. Yeah, that's right. So with that homework exercise, show this. Yesterday I felt like I didn't give you enough homework. Today I'm feeling like I'm giving you too much.
Yes.
But hey. All right. What does this mean? Well, it means that if omega is an eigenfunction, well, not an eigenfunction, but an eigenform of delta with eigenvalue lambda, then it is an eigenform of delta t with eigenvalue t minus 1. Okay? So basically, if I just scale my metric in this stupid way, I haven't actually changed my eigenfunctions, eigenforms. I've just moved my eigenvalues. In particular, I might be interested in the limit where t goes to 0. What would happen to all my eigenvalues? Any takers? They would be really large, except for one eigenvalue, well, a number of times, the 0 eigenvalue. So the 0 eigenvalue would stay exactly where it was, but all the other eigenvalues would become very large. See? So this is great. So this would send all eigenvalues . So what are we doing when we scale the metric in that way? Well, the thing that we're doing is scaling the volume. And I just spend 1 second on that. So, proposition, the Riemannian volume, this is the Riemannian volume with the metric Tg, so this is the volume of X. So let me write this in a slightly more civilized way. So the volume with the metric Tg of X is the integral dg, and this is the same as t to the n over 2 over the integral of x of dvg. That's from the formula that you were going to prove as homework, which I wrote down. And therefore, this is the same as t to the n over 2 of the volume of x with respect to the metric g. So if I'm trying to make my eigenvalues become really large, at the same time, I'm trying to make my volume become really small. All right? So there you go. So t to 0 is a small volume limit. And this is useful and restrictive. Okay. None of this, as I said before, none of this scaling affects the harmonic forms, so the harmonic forms end up playing a rather special role.
This n is the dimension of the manifold, right?
Yes, exactly.
Okay, and what happens in the limit when n goes to infinity? And at the same time, t goes to 0. There is such a limit?
Well, they're both heading the same way. Small numbers raised to large powers are smaller numbers. So anything below 1 raised to a power is smaller than so. Right, so that's our lightning course on Riemannian geometry. There's no geometry, it's just the metric. Everyone happy? Because I'm going to be able to quote you. All right, now we're changing tack.
This dot in your Laplacian, what does that mean?
It means I'm too lazy. What it means is that you get plus Ricci plus Riemann. And I'll actually fill it in. So what I'd like to do now is to mix everything that we've been doing and introduce a few more things which are that was the that actually, what we just did was the 5-minute introduction. All right, so now what I'm going to do is I'm going to really take a hodgepodge of everything that we've done. We're going to sort of look at topology, we're going to look at differential manifolds, and we're going to look at metric Riemannian manifolds, and we're going to sort of try to see, well, really, really briefly, how each of them can give us information about the same objects. And so it's next. So we start. So this part is called homology and cohomology. All right. And I'll start with homology. Okay. So as usual, X is our nice manifold, etc., compact. You can have boundary, I don't mind this time. So we let Ni be d-dimensional just for concreteness, if the dimension of X is n, I want p to be less than or equal to n. Submanifolds. So a submanifold, we have a manifold with its chart analysis. A submanifold simply means that there's a subset of the original topological space for which these charts analysis will also work. So we'll take it to be a submanifold. And then that's that. Definition. I take these to be smooth, by the way. There are other ways of doing this, but this is probably the quickest. A P-chain, AP, is equal to a sum coefficients of these submanifolds. So I've got these set of submanifolds. I just want to sum them. Okay. And I can allow for coefficients, and depending on the coefficients, so Ci could be basically R, C, Z2, Z, whatever you like. I mean, we'll fix some choice, take a choice of these, and then we have that. Now del, which looks awfully like something that you know, is unfortunately being used for something else here. So del is the operation which gives us the boundary. It's the so-called boundary operator.
Sorry, I don't know. You are making a sum of value of manifolds. I don't understand what that sum means.
Yes, I'm taking a sum of manifolds. I'm taking a sum of manifolds. Okay, so take this as a virtual object for the moment. Okay, just go with me and you'll see what happens.
Okay.
So what you can do is you can think of this as just a set of objects, right? Manifolds with coefficients attached. So, so delta gives us the boundary. So I'll give you an example. If we have a line like this, we have from A and B, then the boundary operator, as usual, we worry about orientation, so we have the point at B, this point minus the point at A. So there's the point at B minus the point at A, right? So boundary of a circle is the null set, 0 in this case. How about the boundary of So how about the boundary of this? Well, there's always this problem of orientation, as we keep saying. So if we take our orientation to be such that things point inwards for the inward normal, then the orientation here is this way, which is the other way. Right? So they have the opposite orientation. So you have to. In this case, I would take this circle at 1 minus the circle at 2, say. Right?
So over there it's B minus A.
So here it's the point, well, yeah, it would have been A minus B, the way I've defined it. Up to science, but anyway, it's a convention, you choose. The boundary then of this P chain, so this object where we sum over the P-dimensional submanifolds, is just the sum of the boundaries. It does not act on the coefficients. Okay. And as a boundary map, it has this nice property which is the same as d squared, which is the boundary of the boundary is 0. So, for example, if you take a disk, if I ask you what is the boundary of the disk, you would all say, that's easy, that's just the circles. They oriented that way. If I ask you what's d squared of the disk, well, you'd say, well, the first d gives me this, the second d is still to be applied, and the boundary of the circle is this. So it's 0, so there's nothing there. All right. So here's another definition. A p-cycle is a p-chain without boundary. So in particular, d P, so is null. Then AP is a P cycle. Okay? So that would mean that all the submanifolds which go into defining AP, none of those guys have got boundary. So another definition. ZP is the set of AP such that EAP is empty. That's the cycles. I should call it that. And PP, not the petrol company, is the boundary of a P+1 chain. See, clearly, if I take a P+1 chain and take the boundary, then what I would end up with here is something which is a P chain, right? Because I drop a dimension, so I get P chains. And clearly, if I take the boundary of the boundary, I get 0, so this is an interesting object. And this lets me now run into define the P simplicial. So, as I said, there are many ways of doing this. This is the smooth way. There are singular ways of doing it too. This makes more sense for us. Homology group of X, and it's defined as follows: H, E, X with whether we put over R, C, Z2, Z coefficients is the same as the quotient like that. So what does that quotient mean? What it means is you have chains in here, and right. So these are chains. So we have P chains in there, and their boundary is empty. But when you have something like this, you say, okay, if I have two of them, if AP and AP prime, and A prime P, sorry, are both in ZP, and AP is the same as AP prime plus the boundary of something higher, then as far as we're concerned in the quotient, they are the same thing. Right? So that's the equivalence relation that we're actually using. So at this point, AP is the same as A prime P. And only one of these lives in there. Okay.
George,
Yes, please.
what is an homology group?
Sorry.
The homology group, the definition.
Yes, it's a group under addition.
What addition?
Of cycles. I mean,
You didn't never define what in that sense this was an addition.
wow. Do it in the most stupid way. C1 N1 plus C tilde N1 is the same as C1 plus C tilde N1. All right. So I wanted to draw pickies for you because I think it's easier to have pictures, except I changed my notes. So here we were looking for objects which a P cycle. I said, well, that's That's got no boundary. Here's another one which has got no boundary. And here's a genus G surface. This is the same, right? These are the guys that we keep running into. And this is also no. Okay. So let me give you examples of this stuff. Suppose it means this is the way I've defined it, that these are submanifolds. There are other ways of doing this, and you change this word. Okay. So take your Riemann surface. Let's take a torus, and consider that on that circle on the torus, right? Now that circle is closed. D of that guy is 0, so we're happy. So D of that circle is 0. So you think, ha, I've got somebody who's living in here. But that's not true, because after all, this thing bounds a disk inside the same space. So this circle is actually itself the boundary of the disk. Okay? And we're quotienting out by these guys. So this is equivalently null under that equivalence relation. So it's not there. So something like this is empty. That guy gets eaten up in this quotient. Okay, can I give you something which does not get eaten up in the quotient? And the answer is yes, I can. Here we go, take this circle. Clearly, D of this circle is also, circles have no boundary, but it doesn't bound anything. Does not bound anything on this torus, does it? There's nothing you can draw which it bounds. And therefore, it is a non-trivial element inside this group. In fact, inside H1. Because it's a one-side. So, that's one thing. Suppose I take this guy here. It looks like I've got another one. That'll give me 2. But that's not true, because these two are related by a cylinder, right, which lives inside the space. So the boundary of the cylinder is one of the circles minus the other one. Take this guy to the other side, and you get that. And so, as far as the equivalence relation is concerned, these are actually the same thing. Right? So it doesn't matter which circle I draw around here, they're all the same circle as far as the homology is concerned. Okay? Well, that was cycles. Let me take an easier example. Suppose I'm on some manifold connected X, and I ask about a point. What's the boundary of a point? It's null, right? There's no boundary to a point. So that's pretty good too. So D of a point, null. So can you write the point as the boundary of something which is a submanifold in this space?
How about X minus 1? Would that be allowed?
I don't think so. I mean, in this case, that's too big a dimension. I mean, if you were, sorry, if I was drawing a line, you'd be okay, but I didn't want to do that. So, no. However, any other point is a good point. But every other point is connected, because I said X is connected by a line. There we go. And therefore, every other point in the homology is equivalent to the point that I first thought of by the same argument. So you've just proven a theorem. H0 of x is R. Or R. Because the only element in this thing is 1 point. The only coefficient system that I've got is this coefficient system, so if it's of R, it's R. If it's of C, it's C, so on and so forth. Okay. So then I slow dimensional examples. And I now, how much time do I have?
Minus
2 minutes. Okay. All right. So we have ways of dealing with these things. Just not to confuse things, or maybe I will actually confuse things. Do you know what homotopy is? One person knows what homotopy, 2, 3, 4, 5, 6, 7, 8. Ah, now they're becoming honest. Here we go. Nathan, he's lying. He knows. Okay, homology is not homotopy, and I think the best example is this one. Just to keep in your mind that they're not the same thing. Take a genus 2 surface. I'll just do this because very often I find people find it difficult. Take this curve here up and take this one just here. Oops. There we go. It's at the edge of the diamond. In homotopy, they're not the same. They're not the same because in homotopy, what you try to do is you try to roll this thing as a rubber band across to there. But the only way you can do that is to break it. There's a hole there. You've got to break it, pull it out. And so these are not homotopic. But they are the same in homology. They're the same in homology because if you look at that, they're the boundaries of an object. Even though it's got a hole in it, it's just a submanifold, and they're related by boundary. So the boundary of this guy is one of the circles minus the other one. So they're the same in homology, but they're not the same in homotopy. Homotopy is a finer object. It knows more. And because it knows more, we won't be dealing with it. Okay, this lightning course on homology. And now I want to pass to the second part of that thing, which is cohomology. Oh, sorry, I need a definition. The Betty number, so this is the Betty number, is the real dimension of HP of X with values in R. Okay? That's the Betty number. It's a topological number. Even though I took these things to be smooth, as I said, there are other ways of defining this. This is just convenient, such that you're basically working at the topological level, and you can show that all the various definitions agree, and this thing really tells you something about the topology of the manifold, and doesn't really require any smooth structure at all. I should say that you can very easily calculate the Betty numbers for the torus, because, well, we already know that H0 is R, so the dimension is, the real dimension is 1, right? So we already know that B0 equals of X for any connected X is 1. Connected, remember connected, because there are 2 bits to it, B0 may not be 1. So B0 of x is 1 for every manifold, so we know that's true for the torus, this torus here. If I want H1, I said any circle like this can be written, is not the boundary of anything, and all of them, it doesn't matter where I put them, are the same circle. There's another set of circles that I could have drawn. Which are the circles this way. And there's only one of those two for the same reasons. If you take another one which is slightly bigger, then it looks like you've got something. Let me draw that. These are the 2 circles. This is also a cylinder, it's just I've drawn it in a different way. And therefore the boundary of this object is the difference between that guy and that guy. So as far as we're concerned, if there's a second circle out here, they're the same circle in homology, right? And then you can show that any circle you draw is a sum of the ones that I've just drawn. It's very easy. Try drawing anything, and you'll find that they're all can be written as sums of the ones that we've just drawn. And therefore, we've just shown that there are only 2 independent elements of the torus. E1 of the torus. And you can keep doing this for genus G as well, figure it out. Okay. Now, in the last 10 seconds, we'll do cohomology. Definition. Now, Z with T upstairs. It's a nightmare. Homology is labels down, cohomology labels up, okay? So Z with a P upstairs are the forms, P forms, such that they're closed. So omega P is an element of omega P. And this means closed. That's just the word. So we're looking at the set of closed P forms. Okay? And BP, again upstairs, are all those P forms that can be written as the D. Well, we know D takes a lower degree form and gives you +1, right? So what we need here is a form, let's call it alpha P minus 1, for all alpha. Okay. Then the Pth Durand cohomology group is defined by P upstairs. Remember, cohomology, everything's up. X is equal to ZP X. Now, this could be with C, so we would actually allow for addition of forms under C, complex forms and so on, or other things. So, and it's quotient. And in this case, the quotient is, so if omega, d omega p prime is equal to 0 and d omega p is equal to 0, then they would both be in here. But if they're related by the d of something, so if omega p prime is equal to omega p plus d of alpha p minus 1, then as far as we're concerned in the quotient, omega p prime is actually equal to. Right, so that's the definition of the cohomology. There are a whole bunch of theorems which are known as Durand's theorems, which which basically say the following. I won't prove it. there's a quasi-proof in the notes if I can ever get them to you. It's just we're running out of time. So, Durham claims the following, that there is an isomorphism between the real HP down and the real HP up. In particular, this implies that you can calculate the Betty numbers any way you like.
They give you the same topological information, the homology and the homology?
Yes.
Does that change when it's exact?
Yes. Well, sort of. I mean, depends on what you want to do. If you take a complex manifold, you can still think of it as a real manifold. Nobody stops you. So you can actually go through this whole thing and do it again. Every new structure that you put into a manifold can either be a dud, a waste of time, or it can allow you to refine things and learn more about stuff. I mean, here, even though I was using smooth sum manifolds, I was insisting that this thing is really a topological object, whereas this really requires a smooth structure. I don't even know what D is unless I've got a smooth structure. So I'm really saying that I can use the smooth structure to tell me something about the underlying topological space. And that's the thing. Smooth structure is more structure, so you have more control. Okay? So that gives you power. And once you know something like this, you can play games. If you happen to know what the guy downstairs is, you automatically get the guy upstairs, vice versa as well. So you can move yourself from one to the other. Okay, so I just want to take the next 5 minutes to prove the Hodge theorem. Well, not really prove it, but state it, do a few simple proofs, and then there's, you see, at this point, we've just been dealing with D. But on our smooth manifolds, what we learned at the start of the lecture was that we have this other object, which is Laplacian. Right? So very often you think, hey, hang on, Laplacians, they give me information. So I also said to you harmonic forms, that is, those forms which the Laplacian acting on the form gives me 0, so 0 eigenvalue. That required that D of the form was 0, and the adjoint was also 0, but don't worry about that for the moment. But D of a form is 0 should be ringing bells. Just about now. Okay? Just there. So let's do a little bit of Hodge, and we'll call it quits for the day. So Hodge. So the theorem is the following one. So a theorem X, a compact, closed, Riemannian, I've written it like that, manifold omega P form, and I'll take it to be real just to save myself some bother again. Like that. And then one main right. Omega P is the D of a form which which must be of degree p minus 1, it is the delta of a form which is of degree plus 1, plus it is a harmonic form of degree p. That's an amazing theorem, right? It tells you that you can always write anybody as d of something, del of something, plus a harmonic piece.
Does this theorem have something to do with Helmholtz theorem? Helmholtz theorem? Helmholtz theorem. The Helmholtz theorem which states that a vector can be written as a gradient plus a
Helmholtz. Sorry. Yeah, I mean, if you do that, if you go to one forms, you find that. In fact, in two-dimensional space, even though this is the derivative of a function, this looks like the contraction of a two form, but a two form is really a function. Because in two dimensions, star of two form is a function. And so you can rewrite this as d mu plus epsilon mu nu d nu. So d mu for one form in 2D is d mu of 5 plus epsilon mu nu d nu of g. Anyway, so that's a great theorem. It's called the Hodge decomposition theorem. Great. Took Hodge, I don't know, about 30 years to prove this. It'll take us 5 seconds to... I lost the page, sorry. I'm a bit disorganized because I've changed notes. All right. I'm not going to prove the theorem. I mean, like, it's a lot of analysis, essentially. So I don't like analysis, so we'll stop right there. What I will do is show you that this is an orthogonal decomposition. So, and orthogonal with respect to what? Well, the only thing we have on our Riemannian manifold is our Riemannian metric and our Riemannian inner product. So it's an orthogonal decomposition with respect to that. Okay? So let's prove it. So suppose I ask you to consider the inner product of this. Right? These two guys appear here. So now I want their inner product. They're both degree p because I have an equality here. Now, if you can remember what was written over there, you'll remember that I'm allowed to move that delta to this side and call it d. And by a famous exercise, which you all did last night, except for him, where were you? You remember that d squared is equal to? 0. Thank you. So therefore, we've just shown that this is, it's very quick, wasn't it? So let me stick in the d squared alpha p minus 1 theta p plus 1. Just by using d alpha gamma. Gamma appears there. Somebody think of something else. Sigma, fine, thank you. Sigma, right, by definition. So we just use that. Likewise, so these are orthogonal. Okay? How about this guy and that guy? Well, let's try it. D alpha p minus 1 gamma p. Well, this is the same as alpha p minus 1 delta gamma p. What did we prove about the harmonic forms? They're killed both by d and delta, right? So what's this thing?
0.
So this is? And all right, sorry, gamma p. And this is 0 because we said that d is 0. So we've just part of the decomposition which was interesting for us is that it is an orthogonal decomposition with respect to the Riemannian metric. Okay. So now I'm going to relate this to cohomology in the last -3 seconds. Am I allowed to take an extra 1 minute, 2 minutes? 1 minute. Nathan, can I steal a minute of your lecture? Okay. So definition, HP delta is the set of forms such that they're harmonic. So these are the harmonic forms. And there's an isomorphism. So there's an isomorphism between, I'll leave this as a little bit of a homework for you. Right, we're halfway there, right? Because if this is an exercise, prove this. This means I can keep my minute. You're halfway there. We know that they satisfy this. We also know that there's an orthogonal decomposition, so if you could write it as d of something, the delta part of that argument, the fact that these two things are orthogonal, tells you that that's not there. So we have that, and so let me tell you that therefore pth any number of x is the real dimension of the space of harmonic forms, which is what I really wanted to get to. So what we've done is we've shown that a topological object, roughly, is equal to something which only requires a smooth structure, is the same as something that only requires a smooth structure, is the same as something that requires a metric. Okay? So we have different structures, and they're all giving us the same invariant this time. Now let's stop.
We have time for one or two questions. Yes.
The last line you wrote, is it a sign of different?
It's a sign that I was getting tired. That's false.
Oh, thank you.
Sorry.
One question. George, you wrote the Laplacian as the sum of d delta plus delta d, and these two objects map on p forms. You showed that this is a positive operator. Now, is there some geometric, some natural operator associated with d delta minus delta d, which would no longer have a positive spectrum, but would also be invariant?
Yeah, so the question was, there was a natural operator which was this one, and I chose the sign because I wanted it to be positive definite. Then the question was, suppose I'm a little bit obtuse and I decide to consider this object here. Is this, for me this is a bit problematic because it's not positive definite anymore, so I'm not sure. I mean, it could be that there, no, I won't even try.
Okay, we'll leave the other question for the coffee break. Let's thank George.